Alright, so now that we're stepping out from combinatorics, we're going to actually step into the world of probability. Now, you still may need to use combinatorics sometimes in probability, but for right now, we're just going to focus on a whole different type of science. Now, this science is actually really cool. It came about when people wanted to talk about what's the probability of having success and what's the probability, or what are the chances of not having a success, and that's where the probability came out in play. Okay, so before we get to sample space, we want to talk about success and failure. Okay, now success and failure are two distinct things because basically success is equal to, anytime you talk about this stuff, success and failure do come into play, because when you're looking for something, that's a success, and when you're looking for failure, that's technically a success, but the failure is just the other part of success. It's the times where you didn't succeed, you actually failed. Okay, so before we get there, sample space, let's talk a little bit about it. Sample space is actually all of the possible situations that could happen. It definitely arrives from the idea of combinatorics, which we're counting items in a set or counting how many possibilities. So sample space does come into play. Where there be one dice where you have 6 possibilities, or 2 dice where there are actually not 12 but 36 possibilities, the idea of probability, sample space, comes from this idea of, like, can you count out all this stuff and work with it, okay? Alright, now usually in the past when I've taught probability, I've started off with success, or probability of an event is equal to success divided by the total amount. But if you start thinking of success in terms of success and the other part, which is failures, which is the other parts where I didn't have a success, you're going to start doing a lot better. So the probability of getting success is you take the total amount of successes that you wanted, okay, and then you divide it by the successes plus the failures. Okay, and let's talk about that one dice for a second. So we know the sample space, 3, 4, 5, 6. Okay, all right, so let's say we want the probability of an even number. Okay, well, if you think about it, there are 1, 2, 3 even numbers, so that would be 3, and then there are parentheses, 3 even numbers plus 3 non-even numbers, which would be our failures, which would equal 3, 6, which equals 1/2. Okay? All right, so setting it up is actually really easy once you have the sample space. And one of the best teachers I've ever had in mathematics was my probability and statistics teacher in college, and he said, if you don't take the time to write out what could happen in sample space, don't even consider the field of probability your thing. Or consider passing it, because if you don't take the time to think about what the actual sample space is of what you're given, you're going to have a really rough time of working with it. Okay? Alright, so sample space, success, and failure right here. Okay? Okay, so now let's take a look at probability of getting a not even number. Okay? Well, there are 3 possibilities out of 6, which is also 1/2. Okay. So what happens is if you notice, I have a success and a failure, okay? So these are actually complements of each other if they add up to 1, okay? So if these two add up to 1, I'm good. And in probability, we want to stay between, our probability stays between 0, let me see, less than or equal to, and 1. So we're going to stay in this fraction realm, or this decimal realm between 0 and 1. If you get outside of it, you did something horribly wrong. But a complement would actually be something that the two probabilities actually add up to 1. So technically, okay, so if I were to write it out, the probability of an even number plus the probability of not even is equal to 1. Okay, now if I just subtract from both sides, the probability of getting a not even number would equal 1 minus the probability of an even number. Okay, which makes total sense because the algebra actually works out that way. It actually works really well. So if you ever want to find the complement, just subtract, or just subtract the probability of what your success was from 1, and you have the complement, which would be the not version of that. And once again, I'm just using even numbers on one dice. You can use any kind of event you want on here, okay, that would actually work out pretty well. All right, now, not gonna lie, the next part is odds, and odds are one of the hardest things to work with. But if you think of odds as the probability of success divided by the probability of failure, okay, your odds are actually greatly increased, pardon the pun, of actually passing odds types questions, okay? All right, so with odds, and pretty interesting enough, you need the actual probability that you want and its complement, and you're going to divide the two. Okay, so let's take a look at this. All right, so in a bag you have 7 blue and 12 red marbles. Okay, so the probability of getting a blue is pretty easy. It's going to be 7 out of 19. Okay, that makes sense. And the probability of getting a red is going to be 12 out of 19. Okay, so what are the odds of getting a blue marble? Okay, so what you're going to do is you're going to divide the 7 19ths, and you're going to divide that by, let's get the divisor in there, there we go, and you're going to divide that by the 12 19ths. Okay, now when you do that, you're going to go and multiply. You're actually going to multiply by the 19th 12ths. Okay, and the 2 19ths are going to simplify to 1s. Okay, and you're going to have 7 12ths. So the odds are 7 12ths. Now, also most commonly known is the colon version, 7 12. Okay, 7 to 12 ratio and stuff. Okay, so that's the actual setup for odds. Now, most common plays you're going to see odds are like Super Bowl winners. Okay, all right, so like let's say that you were picking the odds of winning the Super Bowl. Okay, so the odds of a team winning the Super Bowl are like, let's say New England was 2 to 1. So 2 to 1 right there. So what that's actually saying is that for every $1 you pay, you get $2 back. Okay, so that's what it's actually saying. So that's why you want someone that has a much higher odds right there to get actually more money back. So you would actually pay $1 for 500. So that's what it's actually saying. So technically this is how many times it's going to fail. This is actually the failure, so it's the probability of failure right here is what it's actually working with, but it's actually the payout for odds. So it's a little bit confusing with betting and stuff and gambling, but in actuality the 2 to 1 and 500 to 1 odds are just, you know, how much money you're going to get back based upon every dollar you spend, and that dollar is right there. Now if they said the odds were 7 5, so that means you would have to spend $5 to get $7 back. And if you were to actually divide that out, because that is a fraction, 7 divided by 5, that would be a 1.4 to 1 type ratio. So you'd be getting 40 cents extra for every dollar you spent. Okay. All right. And that's it for probability and odds. I'll talk to you guys later.